Okay, our third talk will be given by Mr. Yixuan Chen. Yixuan received his bachelor degree in vehicle engineering from the Central South University, Hunan, China in 2019. He is currently pursuing the master degree in vehicle engineering with Beihang University. His research interests include energy management strategy of hybrid electric vehicle and the control of automatic transmission. His presentation title is a real-time energy management strategy based on fuzzy control and the ECMS for PHEVs. Let's welcome Yixuan.
Hello everyone. It's my honor to be here for a presentation. I'm Chen Yixuan from Beihang University. The subject of my presentation is a real-time energy management strategy based on fuzzy control and ECMS for plug-in hybrid electric vehicles. The presentation is divided into 5 sections. Firstly, I'm going to talk about something about the background. In recent years, environmental pollution and energy shortage have become common problems for the whole world, and China has pledged to achieve carbon peaks by 2030. Under this background, hybrid electric vehicles have the advantages of strong dynamic, low fuel consumption, long mileage, and low emission. The energy management strategy is the key to give full play to these advantages. EMS can be divided into 3 categories according to the method of algorithm implementation, such as the rule-based EMS, algorithmization-based EMS, and learning-based EMS. Each EMS has advantages and disadvantages. Considering the real-time requirements of the vehicle controller, the research of this paper is based on fuzzy control and ECMS. Secondly, I will introduce the hybrid electric vehicle model. The research object of this paper is a P2 PHEV equipped with 8-speed automatic transmission. The main parameters of the vehicle in this paper are listed in Table 1, and the mechanical structure of the powertrain is shown in Figure 1. In order to simulate the driving state of the vehicle, a P2 PHEV simulation model is built through the Simulink, as shown in Figure 2, which mainly includes 3 parts, such as the driver model, the controller model, and the physical model. Figure 3 and Figure 4 shows the engine fuel consumption rate and the efficiency map of the electric motor. Thirdly, this section will introduce the EMS based on fuzzy control and ECMS proposed in this study, which mainly consists of 3 parts, as shown in Figure 5. Firstly, the fuzzy control-based working mode decision method is introduced. Secondly, the mileage-based SOC reference curve is established, which provided by Internet information, GNSS, and navigation map. Finally, to solve the problems of torque distribution between engine and electric motor, an adaptive ECMS strategy is proposed, and the equivalent factor is adjusted online by a PI controller. Before the torque distribution between engine and electric motor, determining whether the engine needs to be started is necessary, usually by making a series of rolls. However, the rule-based working mode decision method requires lots of calibration work, and it tends to cause the frequent stop of the engine. In this context, The further control-based working mode design method is proposed to solve this problem. The system architecture of the further controller is shown in Figure 7, with 3 input variables and 1 output variable. The first input variable, delta SOC, is the offset between the actual SOC and the reference SOC. The second input variable is the demand torque, and the third input variable is vehicle speed. And output variable mode is the Wheeling value of the vehicle to enter the HEV mode. As shown in Figure 8, the membership functions of the input and output variables are all Gaussian membership function. Figure 9 shows the relation between input and output variables with many further reasoning and algorithms. Further rules are made according to the 3 following principles. Firstly, if delta SOC is low, then enter the EV mode. If delta SOC is high, then enter the HEV mode. Secondly, if the demand torque is low, then enter the EV mode. And if the demand torque is high, enter the HEV mode. Thirdly, if the vehicle speed is low, then enter the EV mode. And if the vehicle speed is high, then enter the HEV mode. Rule-based EMS are usually unable to reasonably allocate the energy of the battery to the entire jury. For example, in charge depleting and charge sustaining strategy, the energy of the battery is first consumed to a certain limit, and then the engine is started to maintain the SOC. Once the vehicle enters the CS state, the engine is started to maintain the SOC under any driving conditions. So, ensuring the engine runs in a high efficiency area is difficult. Therefore, to solve this problem, a mileage-based SOC reference curve is proposed, which is provided by Internet Information, GNSS, and Navigation Map. The SOC reference curve can distribute the energy of the battery evenly among the whole jury. That is, the battery SOC drops to the lower limit at the end of a jury. If you continue to drive after the SOC drops to the lower limit, you will enter CS mode to maintain the SOC and protect the battery life. When the mode decided is HEV mode, the torque distribution between engine and electric motor is the key to affect the fuel economy of the vehicle. To solve this problem, an adaptive ECMS is proposed. ECMS is an online instantaneous optimization EMS, which is derived from PMP. As shown in Figure 9, from a long-term point of view, the electric energy consumed at the current moment will certainly consume fuel at some point in the future. The electric energy stored at the current moment will be consumed instead of fuel at some point in the future. Therefore, the battery can be regarded as a buffer energy container. The main idea of ECMS is to convert the instantaneous electric energy consumption at the current moment into fuel consumption, and then add it to the real fuel consumption of the engine to get an equivalent fuel consumption. The control variable that minimizes the equivalent fuel consumption at the current time is called the instantaneous optimal solution. The ECMS can realize the optimal control at every instantaneous moment and achieving the effect of approximate global optimal control. And based on the simulation model, the simulation is carried out to verify and evaluate the effectiveness of ECMS proposed. For the battery capacity of PHEV is several times larger than that of HEV. Casting the battery in a single WLTC driving circle is difficult. To ensure the accuracy of the simulation result, the 4 WLTC driving circles with a total mileage about 93 kilometers are split together for simulation. The EMS based on further control and ECMS compared with the rule-based CDCS EMS in terms of engine start-stop times, the efficiency of engine and the electric motor, fuel consumption, and torque distribution between engine and electric motor. When the initial SOC is 100%, Figure 10 shows 3 curves. The first one is the SOC reference curve. The Second one is the actual SOC curve under the rule-based CDCS EMS. And the third one is the actual SOC under the EMS based on further control and ECMS. Figure 11 shows the torque distribution of engine and electric motor and the running flag of the engine under the rule-based CDCS EMS. During the CS phase, the SOC maintains near the lower limit, which causes the engine start and stop frequently. Figure 13 shows the torque distribution of engine and electric motor running flag of the engine under the EMS based on further control and ECMS. The actual SOC can fluctuate near the reference SOC curve, and the EV mode is adopted in the low-speed urban condition where electricity is most needed, and the HEV mode is adopted in the middle and high-speed conditions. Compared with the rule-based CDCS EMS, the engine start and stop times are significantly reduced, which improves driving comfort and reduce the energy loss. Figure 12 shows the offset of equivalent factor. The dynamic equivalent factor makes the actual SOC coverage better to the reference SOC curve. Compared with the rule-based CDCS EMS, the working points of the engine and electric motor are concentrated in the high efficiency area, which is beneficial to increase the fuel economy. Figure 14 shows the working points of engine and electric motor under the rule-based CDCS EMS. And the distribution of working point is discrete. A lot of working points are distributed in the low efficiency area. Figure 15 shows the working points of the engine and the electric motor under the EMS based on further control and ECMS. ECMS can calculate the instantaneous optimal torque distribution to ensure the lowest instantaneous fuel consumption. The simulation results of this study are shown in Table 2. When the initial SOC is 100%, compared with the rule-based EMS, the EMS based on further control and ECMS has better fuel economy. Under the simulation of 4 WLTC driving circles, the final SOC difference of the two EMS at the end of the simulation is only 0.03%. The EMS based on further control and ECMS can save about 4.56% of fuel consumption in this driving circle. Table 2 also shows the data of engine start and stop times under different EMS. According to the results, the further control-based working mode decision method with SOC reference curve can reduce the engine start and stop times by 66.7%. Finally, this research reached 4 conclusions. Firstly, the working mode decision method based on further control and can better analyze the driver's intention and effectively reduce the times of engine start and stop. Secondly, the torque distribution strategy based on ECMS makes the engine and motor work in a higher efficiency range. Thirdly, the uniform distribution of battery energy throughout the jury is more fuel efficient than the CDCS rate. Finally, adaptive equivalent factor can help better track the SOC reference curve. That's all. Thank you.
Okay, thank you, Yifan, for sharing your work on fuzzy logic controller based on EMS for HEV. Energy management is always an important part for HEV. We look forward to your new outcoming. Thank you. There's a gift for you.